not. So you have this tech support. Can you check that camera is focusing on the front screen?
Do you want the student camera?
No, instructor camera. Okay, yeah. So, so this is just linear multiplying. This is quadratic equation, right? And this is just a little practice of the trigonometry, which should be not very challenging. So what? By the way, I prefer this purple background a lot, but everyone in previous years were voting against it, telling why it is better. But if you would change, if this year, if you would change the mind, when you will be presenting, if you do dark background, it is visible better. But for maybe for printed notes, if you ever printing, white is better. I don't have problem in the way. So you are aware of 3 ways to predict future. One by evolution operator, another by solving Schrödinger equation in finite differences, or by expanding evolution operator into Taylor series, right? You saw this equation, you already have them somewhere. And the third one is by solving Schrödinger equation. But by now, it looks like a little, I wouldn't say lie or deception, but the picture is incomplete. We were declaring that Schrödinger equation generates waves, helps to predict future, but we didn't have the protocol, the lab manual, how to get wave function of the future with Schrödinger equation. Like in these 2 equations, we have explicitly past and future, past and future. And here, well, I'm hiding Schrödinger equation, but by the end of today's meeting, we will do a hocus pocus with Schrödinger equation that will give us similar style protocol, the procedure, mathematical procedure, to convert the past into the future. So if you are equipped with Schrödinger equation and you are aware of this little protocol, then you can take wave function of the past, with a little 0, do some manipulations and get wave function of the future. The time independent Schrödinger equation that we were quantified last time, that has many solutions, is in between. In order to get from past to the future, in this protocol, you will need to solve time independent Schrödinger equation. So if you recognize pieces of these 2 lines and notations, you also can stand up. If not, if you're not doing so, I consider this invitation to mumble something more. Number of slides will be large, but I will skip some of them, and we need only things that will give us, will help us to go through these things. Anything that you consider irrelevant, just close the eyes and wait until something more important. So what do we see here? Symbols psi capital of position and time, x and t, are known. The energy is likely will be the eigenvalues of energy that come out from Schrödinger time-independent Schrödinger equation. We also kind of know that hypothetically. We never practiced solution of this equation, but we are already acquainted with notation, and we have general idea what it is. Well, some of us were finding these energies computationally, right? And those phi going phi that depends only on position here and there, they are eigenfunctions of Hamiltonian. They are solutions, functions which are solutions of Schrödinger equation. They are time independent, but they use the same set of indices, and there are more than one. And I will repeat the whole procedure. I'm just giving heads up so that you do not feel surprised later. So, and you know symbols of summation and integration. The only unknown thing is this C sub k, right? So, in some sense, the goal of today's meeting is to define what is this C. What is this C coefficient? And in order to pursue this goal, to define this C coefficient, we will need to introduce, assume, discuss one of the important properties of good solution of Schrödinger equation, so-called orthogonality or orthonormality. But in brief, these coefficients C are discrete. They're a set of numbers rather than continuous functions. And they hold signatures, hold traces of the past, of the initial function. And then when we throw in these traces, the signatures of the past into this equation, we multiply it by this time-dependent factor and obtain the future. Okay. So I have summarized the last slide, the outcome of today's meeting in brief. But now we are going to go slowly but surely with the details. So, your favorite equation, your less favorite equation, and multiple solutions. And orthogonality. If you have several solutions, if we multiply them and integrate from -2 plus infinity, if the functions are good, and since we are not mathematicians, we will assume that functions are always good. That product will be either 0 or 1. And if they are not orthonormal, if they do not give 0 or 1, we will have some tricks to mandate them to be 0 or 1, which later on it will be called normalization. Any questions right now? Would make sense, more or less. I was playing lady this morning and was not typing questions, so that I saw scratchy, but hope you will forgive me and understand this simply. So here there is nothing new. Any of you, if needed, could come to the board and explain what it is. So remember last time we were factorizing solution of time-dependent Schrödinger equation onto time-dependent and time-independent part. Right? Time-independent part was left for further solution with time-independent Schrödinger equation, and time-dependent part was assumed to have exponential form, because exponent is so nice that derivative of exponential is exponential. Right? And later on, we agreed that it is energy multiplied by this constant. And I don't remember if I highlighted it well enough, but the energy that comes into this oscillating factor is always the energy that is extracted from time-independent Schrödinger equation. So the meaning and importance of the energies from time-independent Schrödinger equation, that if you are going to predict future, if you're going to construct complete solution of wave function which includes time, then there will be oscillating factors where pace of these complex oscillations will be directly proportional to the energies. It is very natural if you are not happy and if you feel that something is missing. And if you want to articulate it, feel free.
Can you say that again?
Sure. Last, I'm going to go to empty page and then return to here. So last time, we were telling that psi of x and t is, we used like x of x times t of t, right? No complaints here. And then we agreed that instead of this t capital, we will use exponential of something multiplied by t. And then we should, well, it was my task to deliver it, but maybe I wasn't a little quick. It is energy. Energy that comes out of Schrödinger equation, that enters the time part of this factorization. Okay? So from h phi equals e phi, put here and this energy goes right into here, into this oscillating factor. And I just, you may think that I like Schrödinger equations so much that I'm not tired to repeat it again and again. So it's the same as here, maybe with a little bit bigger font. If we find this unknown functions, then those solutions, the functions, eigenfunctions of the equation, will serve as this space-dependent parts. So there are more than one solution, and they come in couples. Function number n of x and energy number n. And they are connected to each other. So if we use solution number n, if you want these oscillations to come with frequency E sub n, then here it should be a function phi sub n. You cannot use different ones. They should match.
So essentially, when we make it time independent, are we making it energy dependent instead?
Yes. Perfect. I never verbalized it this way, but you're absolutely correct. Yes. It's very deep stuff. So, but now you do see that there is only one time-dependent function and one position-dependent function. it's correct, but it is not general. And by the nature of the equations that we are solving, they obey these properties you are reminding me of, like association, commutation, distribution. So they are linear. And summation of two solutions will be solution as well, right? So I will phi m of x times e bar t plus phi with different integers, let's say m x e to the power minus f to the power e m t. So this linear combination will be a solution as well. And one can also put some weights, c sub m in front of them. And one can use different proportions of these coefficients, and this combination still will be a solution of the time-dependent Schrödinger equation. Okay. I always mix how to pronounce it. Particular solution is a summation of general solutions. General is a summation of particular. If you were taking differential equations, you should remember this verbal formula. Particular summation of general. So this one is general, and this one will be particular. Specific, maybe worse. So here I'm showing only two terms. But if you have 100 solutions of time-independent Schrödinger equation, then there will be 100 terms in this expansion. And it will be a solution. Okay. So we have infinite number of solutions. Even if the number of infinite number of solutions for time-dependent Schrödinger equation, even if time-independent has limited, through adding them together and varying coefficients, we will get infinite number of solutions. And now we need to make a search in the space. Which of this infinite number of solutions will match the past that we want to start from? So if you want to go from certain past to the future that we want to predict. So at certain time in the past, we had a specific shape of the wave function. And among this infinite variety of specific particular solutions, we want to select the only one that does match the past. Or if you are taking differential equation, the one that matches initial condition. Okay? So in the language of differential equations, we are solving initial condition problem. So we already know the general solution, and now we need to find such specific particular solution that will match the only one initial condition, the past. So this one is one particular, and we have many of those. Orthogonality, or you'll need this concept very soon. So a little mathematical experiment. Suppose we have two functions. And by the way, if you are taking notes, this stuff that we were discussing a minute ago is much more valuable, is most important in what we did. The rest will be a little easier and less important. So suppose we have two simple functions, like 1 and x. And we do an operation of multiplying these two functions, and then integrating it in certain limit. So what do we get for this specific example if our limits are symmetric with respect to 0? Well, you see the answer, but you can guess it right away. Okay. It's going to be 0. So if there's 0, it means that functions are orthogonal. But it is, I hate it so much. When I came as a freshman, it was a big jump from high school to college calculus and linear algebra. So there are much simpler things. Like if you have two-dimensional space and vectors, if they are 90 degrees, they are orthogonal, right? This is much easier for common sense. And what does it mean if two vectors are orthogonal? Is there a mathematical algebraic way to say it? So A equals AX, comma AY, right? Two components, two projections. B is BX, BY. And if we set up the dot product, A times B will be AX, BX plus AY, BY. So I hope it clicks something. So what will be this product if the angle between vectors is 90 degrees? Some of you were already showing the secret sign of the answer.
0.
Yes. You agree? Dot product of orthogonal vector is,
Yeah.
and it's algebraically. So you multiply first times second at a specific projection, first times second in a specific projection, and then stop. And then you get 0 if they are orthogonal. Now, space of functions has not 2, but infinite number of dimensions, which means we multiply first times second at this point, then at a little bit next point, and add all of them together. So concept of orthogonality for functions is just extension of two-dimensional space from 2 dimensions to infinite number of dimensions. And if you do not believe that it is 0, you can just draw this little 2 triangles. Okay. So this stuff is what we discussed in our most important slide. Do not be scared of these ugly boxes. You already are aware of idea. I will articulate it once again. So particular solution is summation of a large number of terms. And each term, which we can label with index k, consists of solution of time-independent Schrödinger equation, which is phi sub k. The accumulation of phase in a complex plane, which includes the energy, eigenenergy of Schrödinger equation, and then unknown coefficient. It is an arbitrary coefficient if you want to brag and say, oh, I can solve the equation generally. But if you want to match specific initial condition, we need to find the value of this C sub k. So summation of large number of terms, each of which is factor of 3. So we do have a task. I have a task. You just listen and enjoy or tolerate it. Find values of C sub k that will convert this general solution into specific wave function that we can call psi of x comma 0 for time equals 0. If we have certain past at time equals 0, then we can set time equals 0 on both left and right sides. So just plug in t equals 0 here and t equals 0 in the right. So what will happen if the energy is multiplied by 0 here? Exponential into power 0 equals 1, right? I like it. It will be shorter. Instead of 3 factors in each term, it will be only 2, because exponential factor will disappear. Right? And then we do have an equation. So the past wave function in the past is equal to summation of all solution of Schrödinger equation, time independent Schrödinger equation, times unknown coefficients. So if we can solve this equation for C sub k values, and we can call them expansion coefficients. But I do not insist. You can call them whatever you like. So if you will solve for them, then our big goal will be done, right? So how would you solve this equation in the black box? Huh? Integral of only integral? So we intentionally acquired the concept of orthogonality or orthonormality. So right now on the left and right we do have functions which depend on x, right? And our answer will be discrete numbers. So our goal, our tactical goal, is to get rid of dependence on x, get rid of functions. So we need to get rid of functions, but not like, oh, I don't like it and I remove them. But in an educated way, so in such a way that this C sub k coefficients, the expansion coefficients, will carry signatures and traces of our past. So it is our wish on one hand, and we do have orthogonality property on the other. So again, I'm stepping back. I want to get rid of functions. And we do have orthogonality property. What is orthogonality property? If we look on it, I wouldn't say cynically, practically, as users. What does it have on the left and right? Yes, but even more practically and cynically, which categories, like what is on, which objects are on the left and on the right of the equation? I can write it here once again. Phi sub m star x phi sub m x equals either 0 if m is not equal to n, and 1 if m equals to n. So dx. So what is on the left? Functions. What is on the right? Numbers, right? So in some sense, orthonormality identity converts functions into numbers. Good. The only specifics is that it converts two functions into a number. And we, at left and at right, we have one function. So second function is missing. Good. But no one, suppose we have equation 1 equals 1. What if we multiply left and right part by 2? It still will be correct identity. So same with functions. No one will persecute us if we multiply left and right by another function. But if we do it, then we will be able to apply this stuff, and there is a advanced word, convolute product of functions into numbers. Get rid of functions. And see here, generally the number should be different. And one of the functions should have star, which means complex conjugation. So why don't we multiply left and right by function m with star, by function m with star, and see what happens. Function m with star x sin x comma phi m star x summation m c sub m phi should be n of x. And since we are already having this big party, no one will criticize us if we add integral dx up front of each. Like if we integrate, if left equals to right, then integral of left will be equal to integral of right. Correct? So I do not know what to do with the left part yet. But with the right one, I do have very pleasant and even to say aggressive friends. So first, the coefficient c and summation can be placed in front of this integration. So since c is just a number, the commutation rules do not apply there. You can frivolously put it anywhere in the product. Okay, and if I do not know what to do, I'm just trying to practice calligraphy and use it as a timeout to think further. So writing once again, integral dx phi m star. No, it's not phi. Here is psi x not equals summation. Here is n, cn, and here is integral dx phi m star phi n. Now, some of the modern smart phones look into photographs that you do, and at the end of the year make albums recognizing, oh, here's the face that comes up. Here's your friend. So even silly smartphones can recognize friends. Can we, the humans, recognize any friend in this equation?
The last part of the thing.
So what it is? Okay. Excellent, thank you. We confirmed that we humans are better than computers. So this is definition of orthogonality, right? And this can be replaced by either 0 or 1, depending on the relation between m and n. If the indices are selected to be the same, it will be 0. If they are not the same, then opposite. If they're equal, it is 1. If they're not equal, they will be 0.
So, how so again are you allowed to have the dx in front of the
Oh, it doesn't matter where you write
No.
TX, to the left or to the right. I was also insulted seeing it in my undergraduate time, but here's the cynical reason. If the function under integration is so long, you're just getting physically tired and forget to put TX at the end. If you do it right away, then okay, it is there. So nothing else. You can put it in the middle if you want. Then it will be completely ugly. So on the left, we have product of the past multiplied by one of the eigenfunctions and integrated. On the right, originally we had a large number of terms. But now we see that the product of functions is convoluted to a number. And this number, for most of the cases, will be 0. Which means instead of like 100 terms, it will be only 1. The only term that corresponds to these two indices coincide. I think we are done. Well, we will chat about it a little bit more, but it is the solution. So if we so this equation, this part, this left part, right part, will be non-zero only if index n, which is in the summation, is equal to the index m. Therefore, we have to replace n by m and completely remove this part. And completely remove the summation. If you see it for the first time, it can be surprising, but I'm not going to run away. I'll talk about it a little more. Oh, I was doing it previously. So I'm just repeating same things, and maybe we'll express it once again. So summation over n, coefficient n. And here we had the 0 or 1. 0 if they are not equal, and 1 if they are equal. Is equal. So this summation, and by the way, there, since it is a little long and ugly notation, but this notation appears very frequently in linear algebra. There was a gentleman named Kronecker who thought, like, why should I write all these ugly brackets? I can use just delta m n, which will mean exactly the same. So it is a symbol that will correspond to 0 if they miss each other, and 1 if they coincide. Kronecker. And I can misspell, maybe it is Kronecker. So, can we write it this way? Open the summation. C sub 1 times delta 1 m plus C2 delta 2 m plus C3 delta 3 over m, and continue as long as I have questions. So you do know that this symbol will be non-zero only once. Whatever we put as an input here. So as an input for the symbol, we put the value of m. So suppose m equals 2. Then this one will be 1, and those will be 0. Right? So instead of C1 plus C2 plus C3, it will be only C1. So this procedure parses only one out of long list. Okay? And there is a thing that if you are still not happy, there is another way to memorize it. So if Alyssa may have seen it. If a snake see a rabbit, they both disappear. Like if you have summation and delta function coming nearby, snake eats a rabbit and disappears itself. So originally we had summation and delta, and after this operation you have only one number, no delta and no summation. This is all the same stuff. And, I always forget to send you the slides, but I'm happy to. But what you write yourself is much more valuable because you process it with your own understanding. Okay, so after this convolution, we get only C sub whatever index will be the same on the left and right. And now we can read it backwards from the right to the left. So coefficient number n is equal eigenfunction number n multiplied by the past and integrated. So it is a protocol how to get this expansion coefficient. You can call them weight coefficient or expansion coefficients, I don't care. Okay? So expansion coefficients are convolution of the past and eigenstate. And as long as we agree on that, we will have the future. So eigenstate, phase accumulation, and expansion coefficient, which has been obtained via our full protocol. Years, decades, and well, not yet centuries ago, when computers were not as developed, this was the major way to solve Schrödinger equation. Today, we can use other two methods as well, but originally it was the only one. So from the past to the future. I anticipate. Yeah, I think it is the same thing. I was just entertaining myself by covering it. Past, future, expansion coefficient, eigenfunction here and there, and phase accumulation. And those first and second way to predict future, which is what you knew before, and this is what you've got today. Okay, done. So this homework is easy. I'm sure you will do it by Friday, and on Sunday night, like I am expecting the PowerPoint slides. Please remind me, you have my email. If I've already promised some of you to send materials, and I'm a little late, but I do not have bad intentions. I really want to send it as soon as possible. Just send me a reminder if you do not see it next 5 minutes or whatever. Okay, have a nice weekend.
Look at my slides. I don't know if I should add anything. So obviously I have my password here, and then basically what I did was just like break down what each part of the thing meant, and then I added, so I didn't know what the size or the, oh sorry, I didn't know what that meant, so I just added.
Okay, yeah. Nothing bad.
Okay.
It's good. If you can send it to me right now.